Okay, so in this video, we're going to focus on impulse, right? And so again, impulse is one of those words that gets thrown around a lot. So it definitely has a non-physics world definition, but it has a physics world definition. So when a pitcher delivers a fastball, a batter takes a swing, and with the crack of the bat, the ball flies off in the opposite direction. So it is said that the bat or the batter delivers an impulse to the ball, right? And it's really the bat delivering the impulse, but the batter has to swing the bat, right? So impulse is the product of a force exerted and the time over which it acts. Okay, the formula is going to be J equals F delta T. J is impulse, right? It is a vector quantity, so our force is the vector because remember time is scalar. Sometimes though, formula sheets or other books, you'll see it written as I for impulse. And the units are going to be kilograms times meters per second, but sometimes you do see it as Newton times second because it's a unit of force times a unit of time. But if I kind of break down what is a force, it's going to be kilograms times meters per second squared. Multiply that by seconds, and what happens is the s from time cancels one of the s's in s squared. Okay, so here's just two quick little examples talking about using this impulse formula. So it says you push on a 22 kilogram shopping cart with a force of 65 newtons. If you push for 1.9 seconds, what is the magnitude of the impulse you deliver to the cart? So they like to do this. This is just simply added information, so you don't need the mass of the cart. You just need to know how much force you're pushing with and how long does it happen. And so I would say J impulse is equal to F delta T. And again, we're going to assume right to the is positive, and we're going to make that assumption here. So we're going to do 6.5 newtons times 1.9 seconds. And we're going to get an impulse delivered of 12.5 kilograms times meters per second, or you can just as easily write this as Newton times seconds. A lot of times when I'm teaching impulse, I teach it to say impulse is Newton times seconds, but you'll see when we talk about something called the impulse momentum theorem, it's actually just the unit for momentum as well. All right, so the next example says you kick a soccer ball, delivering an impulse of 23 kilograms times meters per second. If the force you exert on the ball lasts for 0.25 seconds, what is the magnitude of the force? So again, we're going to start with our impulse equation. So J equals F delta T. And I'm going to solve this for F by just simply dividing that delta T over. Okay, and remember, delta T is time interval. Okay, and we'll see that pop up when we talk a little bit more about some real world examples. And so I'm just going to take 23 kilograms times meters per second and divide it by the 0.25 seconds. I put a 4, I apologize for that. It should be a 5. Alright, and so it's going to be 23 divided by 0.25, and you find that we applied a positive 92 newtons to kick the soccer ball. Okay. And so when a force, again, so let's talk a little bit more about this relationship with force and changing the momentum and so forth. So when a force acts on an object, it changes the object's velocity, right? Because remember, the force accelerates the object, okay? So there is a connection between impulse and momentum through Newton's second law. Right, and so we talked about earlier F equals ma, right? And so here's kind of the derivation of something here. So we got F equals ma, right? That's Newton's second law. But remember, A is delta V over delta T. So we would say m times delta V over delta T. Now, a lot of times students don't like to work in fractions, so I just say, okay, so let's make it horizontal. Let's make it a line. And so we would say m delta V, and all we do is multiply delta T up. And what do you see pop out of this equation? look, there's F delta t, which is impulse. Now, you see here we have an m delta v. That's not momentum, but that is change in momentum. All right, and so what we've really derived is something known as the impulse momentum theorem. Okay, and this is a very important theorem because it makes this relationship, it gives us a relationship between impulse and change in momentum or change in velocity. Or you can just simply put by saying impulse momentum theorem is defined as the impulse that acts on an object is equal to the change in an object's momentum. Okay, so here's a quick example, and we'll talk here in a minute, we'll talk about some real-world examples. Where does this actually come into play, right? Where is this going to help you as a person? So here you got a force acts on a bicycle for 12 seconds and changes its momentum from 15 kilograms times meters per second in the positive x direction to 38 kilograms times meters per second in the positive x direction. So what are the magnitude and direction of the force? Okay, so there's really two ways to attack this, right, or go after this problem. The first thing you do is you can find the change in momentum, because they actually just give you those numbers, right? So remember, change in is final minus initial, and so our final momentum was 38. All right, so PF is 38. Our initial momentum was 15. And so all we really need to do is subtract those two. And so our change in momentum is going to be 23 kilograms times meters per second. And so that, by impulse momentum theorem, J equals delta P, which means that delta P can also equal F delta T, right? I'm jumping a little bit ahead by showing that division symbol. And so F would be delta P over delta T. Now, just as a little side note, this is actually Newton's second law as well, just written with, written as a relationship with momentum. And so all we have to do is 23 divided by 12, right? Because our change in momentum was 23, our time was 12, and so how much force did we impart on this object? 1.9 newtons. And it's going to be positive because we actually increased the velocity, which means the force was positive. The other way to kind of go after this question is to really just start with that relationship that delta P equals J, right? And so you just say like delta P equals F delta T, and then ultimately you do derive that F equals delta P over delta T, and then this is where you would do your subtraction, 15, sorry, not 13. Divided by 12. So instead of kind of doing it in two steps here, right? This is the two-step solution. This is the one-step solution. Okay, and so you end up with the same answer, right? Because you see 38 minus 15 would be positive. Divided by 12 would still give you that 1.9 newtons that you impart on an object. Okay, so that's just a quick example on this relationship, or because on the AP test and homework assignments, they can ask all these weird things and say, okay, here's some information for you to find delta P, but I'm going to ask you something to do with force, right? Or vice versa. Here's some stuff for impulse, but I'm going to ask you to find like the final velocity. Okay. All right, so now I like to relate this back to real world. Okay, so oftentimes what happens is in a lab setting, you're going to graph a force versus time graph. All right, and so it is easy to see how the force between two objects rises rapidly to a very large value and then drops to 0 in a matter of milliseconds. Okay, now one real world application for this is car as crash test data for cars. And so this data, right, is actually a 2020 Volvo, right? And I like to use Volvos because my last two cars have been Volvos, right? So this is a 2020 Volvo XC90, and Volvo is oftentimes rated one of the safest cars always. So this is actually an acceleration versus time graph. So this is really A versus T. But you can easily change this to an F versus T graph by taking this, so your acceleration is on the Y. So all I have to do is multiply this by mass, and that would give me F versus T. And one thing to note, that this is for the head. So this is from like a 200-page document about this car. And so this is talking about like how does the head kind of accelerate. And this, if you notice, also says resultant. So that's taken into the X, Y, and Z directions, because when you get into an accident, your head bounces around all over the place. And so this is for like if I take all the data from the X, Y, and Z directions and combine it into a single graph. And so the mass of an average mass of the human head is 5 kilograms. So it's basically multiply all these by 5. Okay. So your graph will go from 0 to 50, and note that this is in the time axis here is in milliseconds, right, or times 10 to the negative 3 seconds. Okay, if we do, I'll show you some quick calculations for this, because once you find the area under the curve, you're actually finding the impulse, right? And so we've been doing this a lot over different topics. Now, oftentimes they may ask you to find what is called the average force of the collision, and so all you're going to do is take that area that you just found and divide it by the time interval, right? And we're going to do that real quick. I'm going to show you just quick how this is done, okay? Because oftentimes a force versus time graph does pop up on the AP physics test. All right, so here's how that's done. So you notice this is the impact right here. Okay, and so I'm just going to draw this shape. It's basically a triangle, right? So I need to find the area of this triangle. And so the area of a triangle is just simply 1/2 base times height. It doesn't matter if it's a scaling triangle, obtuse triangle, whatever. As long as you know what the height is, right, this H, and you know what the base is, you can just apply the 1/2 base times height. And so the base is going to be 125 milliseconds minus, and I'm just going to use some estimated numbers, right? So my base is going to actually be 0.0, right, 0.098. Okay, so that's my that is my time interval. Now I'm going to convert this acceleration into force, right? So it's about here. In fact, if you look right here, this tells you it's 42.4 Gs. So I'm going to take that and multiply it by 5. And so that means my height, right, will be 212 newtons. And so that means my impulse for this crash was 0.5 times 0.098 times 212. And so that tells me that my impulse is 10.94 kilograms times meters per second, right? I can use this data to find out how fast is this car going, right? But now for the second part, it says to find the average force. And so what it means is on my force axis or my acceleration axis, how can I find what was the average force, or what area can be replace this triangular shape, right, if I want to replace it with a rectangle. And so all I have to do is take that 10.4 number and divide it by that 0.098 number, and that's going to give me the average force exerted during this collision. Okay, and so that's going to be 106.1 newtons. Okay, and if I take that and divide it by 5, it gives me a better idea of where to put this line. So the green area now represents the average force, right, of this collision. And again, this is where car manufacturers come into play, and they do talk about, you know, how can we make improvements and so forth. Okay, here's just another little example, or more real-world examples. I really get excited about this. I've had in my life, I've had 7 concussions. I had to stop playing really collision sports because of it, and so this is an area that I really love to talk about. So this video seems like it's a little bit rambling. It's probably because it is. So the impulse momentum theorem is the driving force behind many safety features on cars and actually in helmet technology. So for example, when someone gets into an accident in a car, they'll experience a certain impulse, right? So they're going to go from like 50 miles per hour to 0 or something like that. Now, if they hit the dashboard, as in cars prior to the 80s, right, because airbags didn't become standard until sometime in the 80s, 90s, then the amount of time the impulse is acting is less, making the force experienced greater, right? And so if we do that relationship talk, right, so J equals F delta T, J, right, is directly proportional to the force, right? So the more force, the greater the impulse, right? If I also act it over a greater amount of time, it's going to be a large impulse. And then force, and this is the important one for the helmet technology, right, or the car technology, is force is inversely proportional to time. So if my time goes down, my force goes up, and vice versa. Now, what happens is in cars nowadays, they have airbags. Airbags were created out of necessity because their goal of an airbag, right, is to create a longer time interval over which the impulse acts, making the force less, right? So this inverse relationship, right? So if I decrease, or if I increase the time, which is what an airbag does, the force is going to go down, right? And so the goal of the technology, which is airbag technology, helmet technology, anything to do with collisions, right? The goal of the technology is to increase the time that impulse acts, therefore decreasing the force experienced. And so, like I said, you could see this in helmet technology, right? I just give you some pictures here. This is the leather helmet, right? This is what they originally started out in. This is the, they call this a suspension helmet. Okay, you can see there's like a webbing in here. This is, for the most part in my career, this is the helmet I use. This is the Bike Air helmet, right? And so this blue bladder had, like, you could pump air into it. There's a little hole right there where you can pump air in. And I tell you what, it was actually harder. Right, this blue piece, this bladder was actually very hard, so it was like rock on rock, right? And so now these are 2 modern helmets. This is the Riddell SpeedFlex, it's called, and this piece right here is the technology. So they have better foam padding, but this piece right here is able to flex. And this is the Vistus helmet, which is always ranked one of the safest helmets. And so their technology is this layer right here, where these actually like cushion, okay, as much as it can. Again, like I said, this is a very topic near and dear to my heart because of my past experiences due to concussions, and so I'm always, you know, pushing this on things. All right, so here's a ranking task. So this is impulses delivered to systems A through D as described below. Rank the system in order of increasing impulse. All right, and so indicate ties where appropriate. So all we're going to do is FT, right? And so the impulse here would be the full FT. This would be 2F over 1/3 T, right? And so, in fact, I kind of wrote this wrong here, right? So this would be 6T, right? So less time. So and this would be 5F over T over 10, and so that's going to be 50 FT, right? And so then you would also have here 10 F over 1, right? 100 T, which would be what, 1,000 T. So 10 divided by 1 divided by 100. So 10 divided by, sorry, I typed that into the calculator wrong, right? So yeah, so this would be 1,000 FT, right? And so you could see they're actually ranked, right, in order. So A is less than B, which is less than C, which is less than D, right? Because this is 1 FT, and you can see this is 1, 6, 50, 1,000, right? And the main thing is, if you notice here, increase time, right? Increase force, decrease time, which means it kind of, right? Increase, decrease, right? So when you decrease the time, you increase the force. But if I'm, in addition, if I'm increasing the force, I'm making that impulse much larger. Okay, so a lot of this technology has to do with collisions, and we're going to move into now talking about conservation of momentum, and then ultimately looking at collisions.